Today we are going into the Stellar Remnants. In other words, basically, once a star has gone through its life cycle and done all its fusiony stuff, and then what are we left over with? What do we get? What are those things? What do they do? What's different between them? All that kind of stuff. So, your warm-up question for this is that when the sun reaches the end of its life, it will collapse into a and finish the sentence. We've talked about this a bit already, and well, especially if you had the homework from Wednesday, then you should. Well, I guess half of you will have done it. So anyway, because split you up depending on the size of the star. But anyway, so give me an answer for what the sun will ultimately become. Right. So the sun, it will collapse and it will form into a white dwarf. Okay, that's the term, a white dwarf star. So we are going to go into what are white dwarfs, what are other things that other different types of stars will collapse into, and just also a little bit more detail in terms of the specifics of the collapse itself. So, let's start with, again, the low mass stars with the white dwarfs. So, as we kind of talked about this on Wednesday, low mass stars will collapse into white dwarfs. Okay. Now, white dwarfs are, well, there's a couple interesting things about them. So, white dwarfs do not produce their own energy. Okay, so stars produce their own energy. White dwarfs do not. So, they emit light based on their leftover energy from before, from when they were normal stars. Okay, so basically, think of a white dwarf. It's like it's something that's lit on fire and it's still burning because you'd already lit it on fire, but it's not gaining more fire, right? So eventually, it will burn itself out. Um, However, because it's so small, and because again, think of the white dwarf was sort of the core of the star before it exploded, and the core was like really, really hot. So this is why on the HR diagram they're in the bottom left corner, right? They're in that region where they're hot, right? So they do have a pretty hot temperature, but they don't gain any more energy. It's just steadily radiating away over time. Um, Now, normal stars maintain their shape and size because their inward push of gravity is balanced by the outward push of their nuclear energy, right? They're producing their energy through nuclear fusion. That's pushing outward, and then the inward force of gravity is pulling inward. That gives you a balance that gives you a normal star. Now, white dwarfs do not produce their own energy this way, so what's keeping them in place, basically? And basically, the fancy term for this, okay, so white dwarfs maintain their shape through what is known as electron degeneracy pressure. Okay, this sounds very complicated, and again, if you really get into it, it is complicated, but there is a very basic sort of way of thinking about this. Basically, it means that, well, think of an atom, right? You have the electrons on the edge of an atom, and so if you have multiple atoms next to each other, that means you have these negative electrons of the atoms sort of pressed up against each other. So think again, atoms are not actually like this, but if you think of an atom like the standard, there's a nucleus and the electrons are orbiting around it in this sort of spherical shell, you have this sort of ball that is the atom, right? And the outer shell of the ball are the electrons. Again, this is not actually how it is, but you can kind of think of it this way. And then, so what you're doing, in a sense, you're saying, okay, these electrons are not going to like pass into the electrons of another atom. So you can think of it as basically the atoms are sort of stacked on top of each other. Okay, so in other words, the atoms are stacked on top of each other like a solid. Okay, actually, that's a good way of thinking of it. So a white dwarf, because again, the star is gas, right? It's super hot gas. Again, plasma, you can argue that way, but it's a gas, right? So there's a lot of empty space between the atoms and the molecules, well, atoms, in a star. So a white dwarf is basically saying, okay, let's just turn it into a solid. So a white dwarf is basically a solid star, is a way of thinking about it. So it's a solid star, and you've condensed everything down. There isn't really any space between the atoms. So because of this, because you've taken out all this space, white dwarfs are roughly planet-sized like the Earth. Okay, so for example, when the sun collapses into a white dwarf, it'll be about the size of the Earth. Okay, so white dwarfs are, again, size of planets like the Earth. Again, they vary a bit. Obviously, you have a little bit larger of mass of a white dwarf, it's going to have a little bit larger of a size. But that's just kind of how they are. So you have basically the core of a star. It sort of collapsed into this sort of solid mass, and it's about the size of the Earth, and it's also like 30,000 degrees or something. So, yeah. And they just sort of exist. They just sort of exist and sit there for a very long time. So white dwarfs just sort of sit there and exist for a very long time as they slowly radiate away their leftover heat, right? Again, from when they were a star. So eventually, the white dwarfs cool so much that they are indistinguishable from empty space. Okay, because again, if you have like a hot object and you put it in like a room, it will eventually become room temperature, right? So that's what's happening to white dwarfs. They're very slowly becoming room temperature, where the room is the universe. So the thing is, and we're not 100% sure exactly how this works, but all models show that this process takes at least several trillion years. So, in other words, this has not happened yet. Okay, but we're considering how we think this is going to go. This is how this will work. The name for this, by the way. So the white dwarfs distinguish from empty space and become black dwarfs. Okay, so all models show this process takes trillions of years. So there are no black dwarfs in the universe, because the universe is is only 13.8 billion years old. So this is what we think would happen: is that the white dwarfs again would slowly fade over time, but it would take a long time until you get basically this dense solid ball of mostly like carbon and oxygen, because that's kind of where, again, they kind of stop in their fusion cycle. That just kind of sits there about the size of the Earth, and it just exists for trillions of years. So there's your white dwarfs, and eventually becoming black dwarfs. So that's the kind of the end result of sort of lower mass stars. So stars that don't get all the way to the iron fusion. Okay, so the sun, smaller stars than the sun, even bigger stars than the sun, but not the biggest ones, but a little bit bigger. They can still get still end up being white dwarfs. But what about the largest stars, the high mass stars? What happens to them? So the high mass stars burn all the way to iron and then go supernova. Okay, so what's the result of this? Okay, the result of this is not a white dwarf. Okay, so supernova resulting in a neutron star. Okay, they go past the white dwarf stage and end up as a neutron star. A neutron star is what it sounds like. A neutron star is uh let's see. Let me go. So it occurs when the gravity is so strong that the atoms of the star are compressed until the electrons are forced into the protons, resulting in a ball of neutrons. Now, just like how the white dwarf stars, I said they were based on electron degeneracy pressure. In other words, it's just that the electrons sort of create this sort of ball where you can't really get any smaller than that. Well, now you've gotten rid of that. Okay, you've taken all the electrons away, and you're just left with neutrons, and they're neutral, right? So it's not even protons, because protons would have like a positive charge. They'd push away from other protons. That doesn't even happen anymore. So you just have these neutrons that are just solid. I mean, literally just solid neutron particles that are all just stacked right on top of each other. In other words, you've gotten rid of all of the empty space in an atom. And there's a lot of empty space in an atom. So, if you want to think, so if white dwarfs were sort of your solid stars, neutron stars are like your super solid stars. That's not a term. But it's ridiculous that there's, because again, even if you talk about, things that are solid objects, they're actually mostly empty space because atoms are mostly empty space. You've taken that away. Okay, there's no empty space in a neutron star. Neutron stars are around 10 kilometers in radius. Okay, they're not big at all. Okay, so if white dwarfs are planet size, neutron stars are like city size. I mean, well, probably a little bit bigger than most cities, but like large urban city. But like that's for the whole sun condensed into the size of like San Francisco or something. You know what I mean? It's like it's ridiculous. So they're unbelievably dense. You may have heard the thing about how neutron stars are so dense that a teaspoon, I think that's it, of neutron star matter has about the same mass as Mount Everest. So, yeah, that's how ridiculously dense it is. Again, you've taken out all of the you've taken away all of the electrons. You've just condensed it all down. There's no empty space between the atoms. I mean, there isn't really even atoms anymore because it's all just neutrons, and they just sit there. And they also don't have any like they don't really have any they don't really produce their own energy either. They don't do fusion. So they're kind of similar in the sense of white dwarfs about how they have their latent heat. I don't know about like if the whole idea that neutron stars would eventually become like black neutron stars. I haven't heard that before, but that I guess that makes sense. But something is a bit different is that remember white dwarfs are like 30,000 degrees. Neutron stars are usually about 600,000 degrees, 600,000 Kelvin. So very hot on their surface. And this is interesting. And they also tend to have, and this is really strange, so we don't really know how this works, magnetic fields that are billions of times stronger than Earth's magnetic field. Now, we didn't really talk about magnets too much, well, at all, really, in last year, because I kind of ran out of time, and there isn't really any, the standards don't really go into it at all, so, well. But the Earth has a magnetic field, as you know. Now, stars do have their own magnetic fields, and they are stronger than the Earth's, okay? I don't know how strong it is, I can't remember off the top of my head, but it's like 10, maybe 100 times. It's not a ridiculous amount of times stronger. But neutron stars can have, again, billions of times stronger. And you think about and how magnetic fields work is basically it's a bunch of small little currents moving around. And if you have all these small currents moving around, if they sort of line up in a similar direction, you sort of create this magnetic field. Now, the thing is, what are currents caused by? Currents are caused by electrons, right? So then the question is, wait a minute, if this neutron star is entirely neutrons, they're neutral, that there's no charge. How do you create current, and therefore how do you create a magnetic field? And the thing is, we don't know. We literally don't know how this works, but they do. We can measure the field strength of these by based on how they interact with other stuff and things. And it's like they're ridiculously strong, but yet we don't see how that would make any sense. So this is an actual mystery about why they have these incredibly strong magnetic fields. But yeah, we don't know. And some of them, the neutron stars with the strongest magnetic fields, they actually have their own name, are called magnetars. So that's a thing. Again, basically, there's neutron stars with extremely strong magnetic fields, and they can do a bunch of weird stuff with that, and they're called magnetars. That's how strong they are. Another thing that's interesting about neutron stars is that they spin really fast. Okay, so neutron stars spin extremely fast. The fastest one, I believe, spins at about 20. I think I calculated it was 24% the speed of light. So that's stupid fast. Okay, so these things are insanely fast. Most of them are not nearly this fast, but it's like something like, oh, it rotates, every like 600 times a second or something like that. So it's ridiculously fast. And something that's interesting actually from this is that some of them are somewhat uneven. So they emit more light out of one side than the other. Okay, which is very strange, but that's sort of what happens for some of them. And so since it's spinning so fast, what we get is basically, think of it like a lighthouse beacon, right? Where since one side sort of emits light more than the other, as it spins, we see this sort of flash of light, flash of light, flash of light, flash of light as it spins around. And these stars seem to emit light in pulses as they rotate quickly. And these are called pulsars. Okay, because it's like they're pulsing, right? Now, here's something interesting. So, what is the best, most accurate method of counting time? It's the atomic clock stuff. Okay, there's something about how electrons vibrate in atoms based on energy output and stuff like that. It's a very complicated kind of process. That is the most accurate way of telling time. However, the second most accurate way of telling time is pulsars. Okay, so these are actually the second most accurate method of calculating time after atomic clock processes. So that's kind of interesting, that if you want to have a very accurate way of counting time, you look at spinning neutron stars. So that's something it's interesting you can get from that. So again, different things about neutron stars that are interesting in terms of their size and their scale. Now, I want to kind of back up a second and talk about supernovas. So the supernova that results from a high mass star collapsing into a neutron star, it actually has its own name, is called a Type 2 supernova. Okay, so a Type 2 supernova is when you have a normal main sequence large star, and it blows up, and you end up with a neutron star. Okay, so that's your, when people normally think of supernova, that is your Type 2. Okay, you're thinking, well, what's Type 1? Well, it's actually a little more complicated. So, remember how I said that for the letters for the spectral class, the OB, AF, GK, AM, those letters originally came from how we looked at the spectra of the stars, and then we rearranged them based on the temperature. Similarly here, the types of supernova originally came from how we kind of looked at the spectra of the supernova, and then we sort of reclassified them later. So, while there is a Type 1 supernova, that type is further subdivided into Type 1A, 1B, 1C. Also, the Type 2 can also be subdivided as well. The thing is, the Type A, 1A, 1B, and 1C, they all kind of... it's sort of not great, because apparently what we learned is that Type 1B and 1C are caused by the same process as the Type 2, they just look like the 1A. So it's confusing. So basically, when you hear about types of supernova, you generally just hear about type 2 and type 1A. Okay, so type 1A supernova is when, and this is interesting. So a white dwarf gains mass, and so this is usually caused um, by another star being close by, which the white dwarf absorbs part of. Okay, so think about gravitationally. If you have two stars that are very close to each other, you have the white dwarf, and there's a normal, gassy star that's nearby. The white dwarf still has a lot of gravity, so it'll sort of kind of yank pieces of the gas away and sort of integrate it into its own mass. And so what happens is absorbs part of. The white dwarf gains mass until it is 1.4 times the mass of the sun. Okay, so that's sort of the magic number. Is once the white dwarf gets to a mass of 1.4 times the mass of the sun, it will then collapse into a neutron star. Then it will collapse into a neutron star via a type 1A supernova. Okay, so basically the type 1A supernova is when you go from white dwarf to neutron star, whereas the type 2 is from normal star straight to neutron star. Okay, so it sort of skips the white dwarf phase in a sense. So that's the thing that. Oh, yeah, and something I made the mistake there is that it is always written as like Roman numeral 1, so it's like IA. This is 2. This is Roman numeral 2, so it's a bit confusing, but that's so you actually don't rate the number 1, which is again kind of weird, but that's just how it works. So all supernovas, by the way. So whenever you hear what is the definition of a supernova? Because you think, oh, the star exploded. That's a supernova. That's not true. So the main way that it's not true is that, again, technically, when a star like the sun becomes a white dwarf, it's sort of an explosion, kinda, but it's not as violent. It's not, it's gonna, do that really. But it is a release of energy out into the universe. So, it's kind of you define it. But that would not be a supernova. So the definition of a supernova is a star collapse that results in a neutron star. Okay, so that's sort of the definition. You can either go from regular star to neutron star or white dwarf to neutron star. They're both still, they end up with neutron stars. So that's sort of your definition of a supernova. So if you end up with a white dwarf, that's not a supernova. Okay. This limit, by the way, this 1.4 times the mass of the sun, the name for that is, I think it's like Chandrasekhar limit. I think that's the term of it. So that's sort of a name for that, and also kind of why we think, okay, this is what we think for. Again, it's an observed limit where once a white dwarf gets to be larger than that, it's just the gravity's too strong and the electrons don't hold and they sort of collapse into their protons, and then you end up with a ball of neutrons, and there's your neutron star. However, you can go a step further. So, if a star's mass is too great for even a ball of neutrons to be stable, it collapses all the way down into a black hole. Now, the limit for this, I've seen multiple things. I remember learning that it was about 30. So if the star is 30 times the mass of the sun, it will collapse straight to a black hole. Whereas, but I've seen something that says 40 times. So I know this is not known very well. Now, a black hole. Now, okay, so black holes are weird, as you may imagine. A technical definition of a black hole is that of a black hole is a region of space where light cannot escape the gravity. And so this gets to the whole Schwarzschild radius thing, right? So remember the Schwarzschild radius r equals was 2 gm over c squared, right? So that we did this before. That was sort of the radius of your black hole, your event horizon, right? Um, Now the real question is, okay, but like, what actually is it? What is the physical thing that's in there, right? And that's the unknown part. Um, there are three main ideas that I've seen. Okay, so there are three main ideas as to what is actually in the black hole. Well, actually, no. Actually, what is in the event horizon? Basically, what actually is the physical object that is the black hole, right? What is that thing? And there's three main ideas that I've seen. So the first is a singularity. So it's an infinitely dense point where all the mass of the collapsed star is concentrated. So this is, you probably heard of this before. There's a couple problems with this. For one, infinity is not a great thing to deal with. You're saying, oh yeah, this thing's just infinitely dense. It's infinitely small. Like, why? You know what I mean? It's just something about that is just not appealing. Now, granted, the universe doesn't really care about what's appealing or not. It's what it actually is. So, that's something. However, there is an issue with this, and this is sort of the issue of, if you may have heard, there's a whole issue about quantum mechanics and gravity not agreeing with each other. And this is kind of where one of that comes into play, right? Black hole, this whole definition of black hole is purely a gravitational definition of a black hole, right? Now, quantum mechanics, of course, talks about subatomic particles and how they work and stuff like that. And part of how that works is this idea that you can't have something that's infinitely small. It doesn't really work like that. Everything has some sort of space that it takes up. And so this definition of a black hole doesn't make sense with quantum mechanics like at all. So, and this is one of the big things about like, how does this work, right? And so the option that I have heard is something called a quark star. Okay. So basically, it's sort of the next stage down, right? So the white dwarf, you basically had atoms stacked on top of each other. Okay. Next stage down, neutrons stacked on top of each other. Next stage down, quarks stacked on top of each other. Okay. A infinitely dense, but still unbelievably small structure made of quarks. The idea is basically, again, it's the next step down from a neutron star. It still has a physical structure, but not much, right? It has an actual size. It's not an infinitely small point, but the gravity is strong enough so that you still get this event horizon situation, but you have this kind of work that's interestingly. Now, there is a video that kind of goes into this a bit. The video that I posted, the kind of extra video that went into a bit more detail about the stellar life cycles, that channel, Astronomic, they have a video on this. So there's something that's actually really interesting about this, because you may have heard about how one of the issues about black holes, in addition to the singularity idea, is that stuff falls into the black hole, right? And the question is, well, where does it go, right? And so you can't just have like, what happens to it, right? And so one of the ideas is that, well, black holes are actually slowly radiating away over time, and this is sort of a thing called Hawking radiation, which I'm not going to get into right now. There's another video I want to show you later that talks about it a bit. But basically, black holes are not immortal. They do fade. Granted, the scale of this is like, the life. So here, let me kind of skip ahead a little bit. The lifespan of black holes is thought. That's not how you spell that. Thought to be at minimum that. Okay, so in other words, that's that long. Okay, so really stupidly long amount of time. I'm glad that just barely fit on a line. So the idea is that like then maybe okay, you have all this energy, and so once the black hole sort of reaches the end of its life, then it sort of explodes with all of the energy that it's ever accumulated. Okay, so that's one idea about what could happen. Now, the quark star idea sort of helps with that because, and again, this is getting into stuff that we're going to get to later, but gravity distorts time. Okay, so if you have something which has a very strong amount of gravity, it slows down time around it. Okay, and so this sort of gets the whole thing in about the event horizons related to this. If you've seen the movie Interstellar, the whole thing about there's a planet that's near a black hole and how they're on it for like an hour, but like 20 years pass, outside of it. It's stuff like that. So one of the ideas is that this sort of solves that issue because you think, well, wait a minute, if you collapse matter down to the size of like quarks, like you collapse like the sun down to the size of quarks, like that's not a stable configuration. It'll want to immediately explode outward again, right? But the thing is that because of this sort of time change thing, when you're in the quark star itself, it seems like it doesn't live like at all. It seems like it immediately sort of collapses down and then immediately explodes back out again. But because of the gravity being so strong, the time gets skewed so much that from the outside it looks like it takes this long. Okay, so that's actually a way of kind of solving that issue, which I think works. So to be honest, from my point of view, the answer that makes the most sense is this one. This just seems to kind of be the most likely, and that like it sort of lines up pretty well. And again, the video that I'll see if I can remember to link to it when I make the classroom post. I think it's pretty convincing. Now, granted, it's just an idea. Hey, this is an idea. It fits what we know. It seems to work pretty well. But we need, of course, proof that that's actually how it works, and we don't have that proof. So, it's really that was a semicolon that was bothering me. Okay. So, because again, the universe does not have to take the easy route. Okay. So, who knows what the actual option is, but I think the quark star makes the most sense. Now, the third option is it's actually a rip in our universe. So, it's basically a gateway into another universe where all matter that falls in goes into another universe. Okay, so this is when you're talking about multiple universes and how the hell could this work and wormholes and blah, 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 right? So we're not going to really touch upon this yet, but this is, of course, another idea for black holes. The idea that because this kind of relates to singularity, you could say that, well, an extremely dense point in space could literally, like, rip through space. Because space is an actual, like, thing that has structure and energy to it and stuff, and so the idea is that if you have something that's infinitely dense, or at least very close to that, you could literally rip through that and get into somewhere else. So, that's an idea. Again, it works gravitationally, but does that mean that's how it actually is? Who knows, right? But it's an idea. So, there's your whole thing with black holes that are stupidly long and all this time and kind of take where they go. So this kind of gives you your idea about all the different types of ways that a star could sort of meet its fate. And I have a diagram that sort of shows this off. So here we have, again, sort of shows the whole thing. So we have sort of your cloud of gas. It sort of condenses, and see, it often condenses into like multiple regions where there could be multiple stars from sort of one cluster. And you'll get different things depending on what you got. So here, let's see what we have. So here's the brown dwarf. Here's your failed star, basically. You have your gravitationally stable ball of gas that's not fusing, so that's less than 8% of the mass of the sun, in this case. Then you have your low mass stars, like our sun, or smaller. So this is anything that's less than 8 times the mass of the sun. It will eventually, again, go through its fusion process to balloon up to a red giant. I'll get into this in a second. And then it will eventually sort of poof off into your planetary nebula, and then this stuff in the middle, the core in the middle, ends up becoming the white dwarf, and the white dwarf ends up eventually cooling all the way to a black dwarf, again, over trillions of years. Now, this sort of process here is, again, talking about the sort of type 1a supernova, where if you have a white dwarf that's also next to, like, a normal star, it'll sort of, again, siphon some mass away. It'll eventually grow up until it's a certain size, and then I should have an arrow kind of pointing this here. See, if it's 1.4 times the mass of the sun, it'll go type 1a supernova and become a neutron star. Yeah, it should have a arrow there. It's kind of weird. And then apparently, I guess you can also have the unstable, but if it's less than 1.4 mass, it just does like I guess a normal nova and just sort of becomes another white dwarf. I guess I'm not really sure how this works exactly, but yeah. So that's sort of the path of that. However, if you have a massive star that's over 8 times the mass of the sun, it'll become, again, go through your fusion processes all the way to get to iron, and you get to your supergiant stars. Then you go type 2 supernova, basically is, giant, your big boom. And you sort of get your sort of remnant of a supernova. This is the Crab Nebula. And there was I think I mentioned this, there was a type 2 supernova that was witnessed in the year 1054 AD. And that's what we see now is the Crab Nebula. So 1,000 years later, this is what a supernova looks like. Anyway, so this is the 40 solar mass number. Again, I thought it was 30, but whatever. And so if you're less than 40, so greater than 8 but less than 40, you'll end up as a neutron star. And again, if you're sort of like, you could have this sort of this unevenness of your stars. So if you're spinning around, you have an uneven type of light. There's your pulsar. There's also a magnetar if you have your extremely strong magnetic fields. But if you're over 40 or over 30, whatever, you'll collapse all the way down to a black hole. And then, so this is the thing about black holes also is that you gather matter around the black hole, and it ends up spinning, getting really, really hot. This stuff around the black hole is known as the accretion disk. I mentioned this before. This accretion disk is like the hottest of any stable thing in the universe. That could be like several, like tens of millions of degrees, or maybe even hundreds of millions of degrees. And if you remember from the peak wavelength stuff that we did, the whole black body radiation, if you have something that's like 100 million degrees, it will emit X-rays. And so they'll often shoot out as these like jets kind of perpendicular to the accretion disk. So that's why when people sometimes say, black holes emit X-rays, and you might go, well, wait a minute, but like, the whole point of the black hole is it doesn't emit light. So you're right. It's just that the stuff around the black hole gets so hot that it emits in X-rays. And again, just based on the whole kind of... This is all spinning around, right? So think again about how, like, the solar system, the planets spin around in, like, a plane, and, like, a galaxy spins in the same way. So it's all spinning, and it's spinning incredibly fast, hence why it's so hot. And it's sort of, again, it shoots the X-rays off into these jets sort of out on either side. Those are called quasars, by the way. So if you've heard of that term before, let me actually write that in there. So black holes, let's see, matter gathers around black holes in a spinning disk known as an accretion disk. This disk gets so hot, slight edit here because I forgot. I remembered that I originally had a shortcut in place for OBS that it was like, if you press spacebar, enter or something, it stops the recording. And I'd accidentally done that, and I actually messed up a recording once. So I decided, I'm going to change the shortcut to something that I'm never going to press when I'm recording. So I changed it to to this key, the freaking tilde thing. So once I clicked that, I stopped the recording. Thankfully, I was almost done. So, okay, that's a stupid coincidence. But anyway, so let me continue what I was going for. So, yeah, you have these disks there, get to 100 million Kelvin, and they emit X-rays, and they are emitted as jets kind of out of the poles, known as quasars, and there you go with your quasar term thing there, kind of shooting out in either direction. So if you've heard quasar, that's what those are, which is also where the Pokemon Rayquaza gets its name, even though Rayquaza doesn't have anything to do with black holes, but whatever. Yeah. So that's what that is there. So there you go. I'm really glad that was at the very end of the thing, so I don't have to re-record the whole freaking thing. I went to look at OBS, and I was like, why does it say start recording? Oh no, did I just not record this entire thing? But no, I did. So it just the last part, which was that was stupid. So that pretty much covers it in terms of like what we got for all these, black holes, neutron stars, white dwarfs, all that kind of stuff, and now you end up with what you end up at the end. So yeah, your wrap-up question is, what is the specific definition of a supernova? Okay, so your so again, the whole point of this is to say that a supernova is not just star go boom. Okay, there's a little bit more specifics to that. What is that, and what's the distinction between those things? Why is this a supernova but this is not? Right. So what is the difference? Okay, so you may have noticed it when I was through this, because again, I already did this. The recording got screwed up. So a supernova, it's for one thing, it's an explosion caused by a star collapsing into a neutron star. So that's the key. A supernova is a neutron star. Well, it results in a neutron star. A normal, well, not normal. Let me go back to the thing here. Yeah. So getting to a white dwarf, again, you have just sort of the planetary nebula poof. And then again, if you have sort of an instability thing, which can result in a white dwarf, that's a nova, not a supernova. A supernova gets to a neutron star. And this should have an arrow pointing to neutron star. And then here also, for example, this is a wrong thing, having type 2 supernova. Oh, it could be a black hole. No, no, no. If you have a star that goes straight to black hole, that's not a supernova anymore. That's actually a hypernova. And gamma ray bursts, we think, are also kind of caused from that, if you've heard of those. That's something where it's like, we're not 100% sure that's what it is, but like everything points to that being the case, but we don't know it technically, so yeah. But that's kind of what we got for that. So a supernova results in a neutron star. So just be kind of a little bit careful where if you're talking about exploding stars, not all exploding stars are supernovas. Not like the whole Crab Nebula thing in 1054, that did result in a supernova. The star Betelgeuse that, you know, people talk about, oh, it could go supernova. That actually would result in a neutron star, so that is a supernova. But other stuff, not necessarily. So, yeah. And then I think that's basically, yeah, so on to the homework. So, for your homework, I want you to basically draw your own diagram, basically sort of copying this here. You don't have to include everything. For example, the brown dwarf thing, you don't have to include that. And honestly, this stuff with, like, this thing here, you don't really need to include that either. But the idea of, again, low mass star to red dwarf to planet to nebula, white dwarf, black dwarf, and then high mass star, red giant. Here, but don't just perfectly copy this, because again, you have some mistakes, right? So for example, we say supergiant to type 2 supernova to neutron star, then you would need supergiant to hypernova to black hole, right? So there are some mistakes on here and just general stuff. You know, again, don't copy this whole thing word for word, especially you don't really need to. Anyway. So, but I want you to kind of create something like this of your own volition. You could just kind of draw it on paper and take a picture and upload that, or you can, again, make it on just using some image editing software, whatever you want to use, and upload that file. So whatever you want to do with that. Yeah, but that should be it. Tomorrow we are going to get into some math stuff. It's not a ton, and it's actually based off of something that we did in December. So if you remember, we talked about like the luminosity equation. You remember it was this one? Is that? Nope, that's the wrong button. This one. Yes. Remember that? Maybe we're kind of start back with that, kind of mess with it, and get to some numbers that are actually and values that are helpful in terms of talking about like what temperature planets could be, and therefore, like, could they have life on them? So we're getting into that and kind of how that works there. So, I don't know. I think that stuff's it's something where it's not like super easy, but it's considering what you're doing, it's surprisingly easy. I'll put it that way. It's easier than you think it should be. So that's what we're gonna get at tomorrow. So, okay. Hopefully the recording worked this time. Okay. I'm done.